Hi guys, Sajad Hussain again. This time I'm going to respond to one of the questions raised by one of my subscriber. So let's go to the question which was asked on one of my videos. The video is design of an underground concrete water tank with the STAADPRO. This was the first part where I explained how to develop the model and apply the forces, etc. Now the question asked here is how to read the plate stress results in the middle of the bottom slab. How do you calculate the reinforcement reported by the STAADPRO? How do you calculate the one-way shear and two-way shear from the plate stress? Now this is I can understand this is a very basic question, and normally our beginners, our students, they face this problem that okay, they can model the plate element in the stat, but then they cannot interpret the result given by a stat. Why this is so? This is so because most of the students, they do not go to the manual, and they do not try to understand what the manual has given. So I'll explain this with the help of the manual. Here, I have opened the help, and in this help, you can see that I'm going to open the article which is plate and shell elements. Let us start from the nomenclature. As you can see, that first, this set of nomenclature of a plate element is okay, but this is not okay. Why this is okay? Because this is clockwise I, J, K, L, and this is anti-clockwise I, J, K, L. That means either you are following a clockwise nomenclature naming system, or sorry, an anti-clockwise nomenclature or naming system, but you cannot cross them like I, J, then K and L, or I, J, then K and L. That means the number should be either in clockwise direction or in anti-clockwise direction, but they should not cross. This type of element is not acceptable. This is what it is explained over here, that this is okay, but this sort of nomenclature or this sort of forms are not okay. Now, from our basic theoretical knowledge, we know that whenever there is a plate element, the thin shell element, we can say, then the stresses are either normal or shear. If the stresses are acting in x direction, then we denote them as sigma x, and in y direction, which is perpendicular to x, sigma y. These are the perpendicular stresses. And then the shear, tau xy and tau yx. And of course, these shear forces are also acting on the opposite planes, or opposite faces. This is very good explained in any strength of material book. You can open and you can go through it and you can read more about it, that how these stresses are defined, the normal stresses and the shear stresses. Now this figure, which shows the quadratic stress distribution assumed for the bending, this is the mechanism what is adopted for stat development. Here, first of all, I'll explain to this the coordinate system for an element. Mind it, this coordinate system is local coordinate system. This is not global coordinate system. I'll explain this on a stat, that how it is different from the global, and what is the difference between a global coordinate system and a local coordinate system. But for the element, all these stresses, the moment and stresses, they are the stresses are in local coordinate system, and these are shown like this. For example, the shear is Qy, this shear is Qx. The moment in x direction is mx, shown like this. mxy, this is the moment in this direction. Further explanation is little bit down over here, like in this figure. For example, you have the nodes I, J, K, and L. This is in anti-clockwise direction. So if you are moving from I to J, this is the direction which is called X. Then perpendicular to X is Y. This is local coordinate system. And then perpendicular to XY plane is Z. So this is the local coordinate system. And then it is defined as top surface. What is the top surface? It is in the positive Z direction as top surface, and bottom means it is in the negative Z direction. So this is called bottom surface. So the term when we use top surface or bottom surface is does not reflect that this is on the top or this is on the bottom. Rather, it depends on the local coordinate system. So this thing should be very clear to everyone that the top surface means it is in the positive z direction and the bottom surface is in negative z direction. Then the perpendicular stresses Sx is the normal stress in x direction. This is the x direction. Sy is normal stress in y direction, and Sxy is the shear stress shown over here. And then this figure indicates the variables used in STAAD, like SQY. This is the shear in y direction. SQX is on the x plane and this is on the y plane. The moment MXY, this moment is acting on the x plane, and MXY, of course, the opposite moment. This is acting on the opposite side. So this figure shows all the moment and shear forces applied on this element. The concept here, how the moment will be there, so we have to follow the right hand rule. If you see this my, this is the direction of the moment. My will be acting here in this y plane, you can say, and then its direction will be in mx. So that's why this is shown as mxy. This figure is very important to understand the concept of moment, and the tension will be in the top when top means positive z surface. So this is the bending shown where the tension will be on the positive local dash surface. Then the moments are transformed in structures and it is shown like this. And I'll ask my listeners, especially for the beginners, to correlate this figure with Whitney's block. If there is a compression on the top and tension in the bottom, then it is simply a Whitney's block, and then you can apply the equations available over there. This is another direction, local x, local y, local z, and this is the local top surface. It is clearly mentioned over here that this is local top surface, and it should be in compression and bottom is in tension. We assume that this is in compression and this is in tension. So this is the way we can define concrete reinforcement based on the basic principles which we have already learned in our basic concrete design. So concept of moments are here. This is the normal stress. When we say normal stress is on this surface, which is x, xx, sy is in this direction. And these are the shear forces, sxy, syx, very clear. And then this is the shear force in this direction. That means they are parallel to the plane. So this is called SQX and this is SQY. So having a very clear concept from these figures, we can interpret our results. Now, I have used a very simple problem over here. Now, this is a slab which has only 6 elements defined. You can see here at the origin, I have shown the global coordinate system. That means X is in the right hand direction, Y is always upward, and Z is perpendicular to the XY plane. But when you see this figure, now the element number 1, let me show this only element number 1, so it will be very clear. Now element number 1, it shows the local coordinate system I to j, this is x, then of course perpendicular to x is y axis and perpendicular to xy plane is z axis. So all my forces will be shown over here and they are related to this. When we go to post processing, then in post processing you can see either we can check the displacement, we can check the reactions, support reactions, we can go to plate results. Now, plate results, they are shown in two different tables. First of all, this plate result shows the plate center stresses and plate corner stresses. So for the time being, I'm not interested in plate corner stresses, so I'll put this table off. I'll show this one. These are the plate center stresses. These are the plate numbers. We were interested in plate number 1. These are the load cases, load case number 1, 2, 3, and their combinations. And these shear forces, which are shown over here, SQX, SQY, then for membrane, SX, SY, SXY, and the bending moment, that is MX, MY, and MXY. The units are, of course, stresses are in PSI, all stresses, and the moment is pound inch per inch. So that you have to be very careful, and then with the figure correlating to these values, you can interpret the results or you can understand what are the forces for any load case, whether it is SXY, what does it mean, SQY, what does that mean, SX, SY, SXY, etc., moment, etc. Now, once you have defined or you have all these results of the plate, then what to do? Then the question was how we can design that. Either you go to your basic knowledge of concrete design, or what you can do, you can use STAAD to design the plates also. You can go to analysis and design, concrete, and then we can select the code which we are want to follow, say for example ACI 31814, and then we select the parameters, all the parameters are selected, we define the parameters. I'm not going into details and defining all these parameters, so I will close this because it will take by default all these parameters, and then in the command I will add, let me select some, yeah. So here in 318 2008, We can select this or all and say, for example, in the command we can design slab or element, assign, close. Or we can show the whole. Now we can check what is the design element, assign view. Just 1 minute. Let us save. Let's run. Let's see the output. So here you can see that we can check, and as per the design, only the minimum reinforcement is required, and top and bottom the ratio of reinforcement is 0.270. So in this way you can design the elements. All the ACI codes are not supported. Sorry. Now all the elements are selected. I was doing a mistake. I did not press this concrete button, so that was the mistake. So here all the elements are selected. Let me run one more time. So it is done. If I want to see the output, I will see the output over here. And then at the end, you can see all the elements are designed. Luckily here, all the reinforcement are minimum. Somewhere it is a little bit different, but you can interpret where the reinforcement are there. So this is one way of doing this. Pretty easy. But the another way is that you can select an element, and since you know these stresses, the shear forces, the bending moment, everything is known. So you can develop your own equations by your initial knowledge or basic knowledge from the concrete design, and you can calculate the steel. So here are the two ways. Either it's done by yourself, or you can use a STAAD to design your slab or elements. So hopefully I have addressed all the problems over here. The question was related to how to read these plate stress result in the middle of the bottom slab. So this is how it is read, and how to calculate the reinforcement I have shown either by yourself or by STAAD. You can do it. How to calculate the one-way shear and two-way shear. This is related to foundation design. So whenever I will be handling the foundation design, I will explain how to calculate the one-way and two-way shear. So hopefully this answers the question. I'm very thankful to you. Please do not forget to subscribe my channel. Thank you very much. Bye. So let me stop my recording over here.